Okay. Well, we'll see how this goes. This is my attempt at a first online lecture, since we have such a cold weather today that NDSU's classes are cancelled. So, well, let's see how this goes. So, last week we talked about the problem of having certain, here, let's see if you can see this here. Let's copy some, having certain balls connected by springs hanging from each other in a symmetric manner, something like this. And you have some kind of strings connecting them. These are all our springs here. So, something like this. And, well, actually what we did is that they were completely one-dimensional. So, and they were moving up and down. So here's the code that we had for that. I made one tiny little change to the code here. We had this compiling error with nanosleep. Turns out that we didn't have to define the full structure thing here. If you just call time spec, that's already defined. And then this error that we had goes away. Anyway, so this was our code. Let's just briefly go through what it did. So we have our equilibrium that we could define from the analytical solution that we had, where we could define these certain heights as a function with zero velocity, and they should just stay there. We could init, we have this init routine that sets the current, height, and velocity to the h0, v0 values, and we have our force routine, which gives us this this force vector. It's a vector for all n particles, just in one dimension right now. And that force vector is returned here. Now we have our Berle iteration routine, which calculates the force, right? And then it applies half the force to the velocity. Then it calculates the new position by adding dt times this half of the old velocity and half of the new velocity. This is intermediate bit to get a second order accuracy. We calculate the new force, and then we update the velocity with that new force term in here. We'll simplify that a little more later on, but let's just stay with this simple algorithm. We defined our draw routine, which basically just consisted of drawing these circles at with some kind of random colors at position x dim over 2, and then y dim minus this h in a way that's scaled for the window, right? And our actual iteration routine, the main routine, then defines this free draw, this draw routine, and it defines the graph that we can still look at, and it defines, so we have this start menu, we have this falling objects, we could define this double object now, h0, which was the original height, and then we have the initial values, and of h0 and v0, and then we have our integration time step dt. The number np was the number of particles, right? That's a maximum of 10, right? In fact, we should probably change all our things to go to np, right, for the number of particles instead of n. So we just can change the number of particles if we want to np. We can do this here too. And that would allow us to change these at the as needed. In fact, these could also be a function of np only. We only need the number of particles here, right? We do this for np particles. And yeah, so and we can make this a mod. For a maximum number of n particles that we can have. And then we have the free draw, which you can click on, we can see these moving particles. And we have our sleep routine, and there we go, right? So now let's have a look at what happens when we compile this. So this is our CC routine with telling where the include is. This is on a Mac, so it has the X library at a funny position, so it needs another include library for that. And it also has a new library position, but otherwise you need to tell it where to find our special library and the X libraries for this system on the Mac. We can compile this, and we end up with this position here. We have our graph, which now consists of our particles, and we have to allow the h-min to be much smaller. I forget where we had to be this at -50 or something like that, right? To see them all. Yeah, now we can see all the particles in here. And I think we initially set them at these nice positions, and now if we run this, nothing happens because they're all at equilibrium positions, and now we can give this bottom one some kind of initial velocity. This is the bottom one with such a velocity of 0. We can give it a velocity of, I don't know, 10 or so. And now if we initialize it again, then it's going to start to move a little bit. We may have to slow this down a little bit. Yeah, so we have our bouncy initial conditions. Let's init this again. And it now starts, so it gets kicked up, and now these things start to wobble like you would expect in here, right? Now, if we had G at 0, I'm not even sure if we have G in here, so we probably actually move all this stuff out to some kind of init routine, init menu, just to separate these out. If this is the number of particles that you want to deal with, it still makes sense to be able to manipulate these like this. So we can set this back to equilibrium, init equilibrium, init. Okay, and now there's nice and stationary. We could try something else now. Where it's set A0 to, I don't know, 0. That means this one is now going to drop down, and they're bouncing off like you would expect. So all kinds of fun things that you can do. But the key part for today's lecture is that, of course, the particles don't have to, if you think of this like particles actually hanging there, they don't have to hang like this, right? They can actually move sideways as well, right? So what they should be able to do, if you look at this, we can now move things. So they should be able to, this is editing in things, so I should do that. So what we should be able to just do is move, move objects, and they should be able to have sideways or any number of dimensions they should be able to move in, right? And that should be possible to do, that you don't have to move in 1D, right? That's a typical thing. So now the question is, how do we have to adapt our equations of motion? And all that happens is that we have to add in more dimensions, right? So now they have to have 2 or 3 or however many dimensions, right? So what we're going to do now is we're going to move up here, and we're going to add in a number of dimensions, right? So this will a velocity in some kind of dimension d, and this will be in some kind of dimension d, and now we have to define, and I guess we can start in 2 dimensions, but you could make that 3, you can even make it more dimensions if you like, 3, 4, however. Now, the initial conditions also have to exist in g dimensions, right? And these things all stay more or less the same, right? All that we have to worry about now is what are the forces that we have, right? So we have these h's. I'm not sure we use these h's even anymore. So the time we need with these h's, I think we don't even use anymore at this point. So this is just for display, right? Now the question is, how do we want to do? So these are in terms of d, right? Some kind of dimension d. So now we have to have a loop here for this for int d equals 0, d smaller or capital D, d plus plus. And I think what we want to do is just if that's the 0 dimension, that's, well, it depends on how we want to count this. In one dimension, let's say the first dimension, we make it this. For our equilibrium, the direction that G happens to point in, and then else H0 D equals 0. So there's no extension, so then it will be exactly the same as before. Now that just we count the first dimension as the downward dimension. I guess we can pick up what coordinate system as we like. And V also now has d dimensions, velocity, right? In it, now the same thing applies as before, except now we have to have also the dimension d. And it's nothing happens here except that now each of those has another dimension here, d. Okay. Now, F is this forcing bit. It has a number of particles in there, which is fine. But now it also has to have a dimension d, right? So the forces will be in d dimensions, right? And now we have a bit of a, we have to think a little bit, because if we have, let's just do at the simplest case, let's just copy this. We have 1, 2, I don't know, something like this, 3 particles. The forces depend on the actual positions of these, the actual displacements that we have for these particles, right? So we have to have some force. The force will be in this direction here, right? And similarly, the force between them will be in this direction, right? So there'll be a downward force, which is just G, right? So we have a force, so we have a force G pointing downward, then we have a force from the one string and a force from the other. So we have to now make sure that we look at this in however many dimensions that we're looking at, right? So generically what's going to happen, this will depend on the magnitude of the displacement, right? The force are typically the central forces. They'll be in the direction between exactly those 2 points. They'll point in this direction, and the magnitude will be whatever the force law is, right? In one dimension it was straightforward, but now we have to add them up as vector force components, right? So now we have a displacement in the x and in the y direction, right? And we can get the total displacement as always as the square root of this squared plus that squared of all the dimensions, right? Now, how are we going to do this? We now we have these previous positions, right? HM now was the height of the previous wall, which now is a function of the dimension d, right? So again, we got to do the special case for the first one. There is no one above it, in which case we said now we have HM 0 equals h0, and I guess we should do our loop again for int d equals 0, d smaller capital D, d plus plus. Then we said that we get here hm0 hmd. So now we're going to say if d equals 0, then it will be h0. Otherwise hm is 0. So that's the first particle, which basically, this is just like the point it hangs from. So at this point we have one bit which goes from here to some kind of ceiling here, right? So we assume there's some kind of ceiling sitting here that this is hanging from. This is the point of where that ceiling is, right? So this, we set it at the height of h0, and the other dimensions are all 0, right? This is our initial point. This is what we have here for the initial point. Else, we set them at the actual h positions. And now this also has to be a loop. Else is just whatever this hm d is just this hn minus 1 d, just wherever this thing lies. And now we have this double HP. This also has to be a d-dimensional vector, so this has to be capital D. Same thing here. I hope I haven't done it wrong too many times. This is capital D, of course. In the definition, so we have HPD, right? And now if n is, so for the very last one, we don't want there to be a force, and we just set this to the previous one. So then if n equals 1, then we have another loop for all d. This HP of d is just the n. So this is just the very same position. Otherwise, and then we need another loop for HPD is just this D, right? Now we come to the actual bit, which is where we're calculating the forces, right? And now, of course, this has to be an object that depends on the dimension. Now, our forces, the way we wrote them here, they have a direction that depends on the vector direction now. So no longer in one dimension. So we need to have a sort of distance vector, right? And we can write here all these things d1 of d, and we need a d2 for the second vector of d, something like that, right? And okay, then we have a d2 force as well. So with these force vectors, now the question is how do we apply these forces? So we know the magnitude will depend on the total distance, right? So let's first calculate d1, right? So now we have d1 of d equals h n of, actually let's do hm, the minus 1 of d minus hn of d. That's the displacement 1. And the displacement 2 is, so this was the displacement 1 right here, for this term here. Now we're going to do this term here, this displacement. So this would be displacement 2 of d equals h n of d minus hp of d, right? In fact, we should be a little bit careful. So if we define our displacements, they should be completely symmetric. So the order now matters a little more. So here we've taken them this way around, this way, to already take into account the vector nature of the force, right? So we have the magnitude and the vector kind of taken into account here by changing the direction. Now here we have to be a little bit more careful. So we want to define some distance, and this would be, so the force acting will be in the direction of our position, the position of the particle that we're interacting with, minus our position. Right, so let's do this way as well here. Particle that we're interacting with minus the current position. That is now the displacement vector, right? So now we have the displacement vectors, and now we want to find the magnitude of that, right? And the magnitude of the force, we say, is proportional to the displacement that we have. So how do we do that? Let's define the absolute value of that, which would be square root of d, well, let's do, in order to calculate that, let's first do 4 this is generically for any number of dimension. Let's set this thing to 0 first. d1 plus equals d1 d times d1 d. So this would give us a scalar product of that vector, right? And then we can get the absolute value taking the square root of, and there may be ways of making this faster, but this is just very practically. So we do this for d1 abs, so this then gives us the absolute distance, and we can get the second bit, which is the d1 abs distance again, right? This is now the one for the d2, and this is exactly the same thing, only for d2, right? And this then tells us d2 abs, right? Okay, so far so good. So this gives us d2 abs. Now, the question is, how do we move on from here? So now we have the absolute distances and we have the vector direction. So what we ought to do is, the force is this absolute, let's just write this down in a stupid enough way. So this would be d1 abs. This is k over m times d1 apps. Now we need to have the direction. So this has to be for all dimensions, right? So now we have to do for we do the same thing here. Now we have this abstraction times this d1d, but this vector needs to be normalized, so it needs to be divided by d1 apps. And for these quadratic forces, you'll see that something very nice happens, which is that d1 apps doesn't even come into play here. So that's so obviously for efficient code, we don't even need to calculate d1 apps for the quadratic forces, but that's very, very specific for the quadratic forces. And we'll just leave it in here in the general case, right? We also need to find the g forces, right? We can't just say plus g because that happens only in one particular dimension. And so now we're going to do for in d equals 0, d smaller d plus plus, g f of d equals, well, maybe we'll do a special little command here. This is fun in C, so we can do something. If d equals 0, question mark, then we're going to get the value of g here. Or else we're going to get the value of 0. This is a fun little C utility, so that it means if d equals 0, this will give you g, otherwise it will give you the second bit. Just a nice shorthand way of doing this. So now we have the g force defined as well. So now our force consists of this plus the g force of g. And here we have now the same thing here. So this is times this times d2 apps times d2 of d over d2 apps. So this should now be the forces in d dimensions that we get. Now our iterative routine, it has the positions in d dimensions and it has the velocities in d dimensions, right? Oh, and this is capital D, of course, not lowercase d, because that's our string define term for this. And fd. So now we calculate the force. And all that happens now is we do this for all particles, and we do this for d equals 0, d smaller d plus plus. In fact, we can leave this one out and then put the bracket right here. And we do this at dimension d, this at dimension d, and then we apply to that velocity the force for that dimension, and the position vector also applied at position d plus dt vn d, right? Then we do it again, and we apply the same thing for n equals np, and now we have to do this for all the dimensions again. Yeah, d smaller d, d plus plus. Okay, and now we do this for all, we apply this velocity at d, and d here, and another d there. Okay, so now we've applied our velocity terms here, and we have the velocity, the original velocities here, they get updated with half the forcing. Now in d dimensions, the positions get updated in d dimensions, and now the velocities get updated again. Now we need our draw routine, and all that happens is that we take this hn, right? Now we have another x dimension, and so say that our 0 dimension is still the downward dimension, and our 1 dimension is now the x direction. And we are going to say x dim plus 2 plus, so this will be hn 0 direction, and then this will be the hn 1 dimension. Now, of course, it has to be two-dimensional for this code not to crash, or we could have a routine that takes care of this, that it requires this to be d larger than 2, right? And so then this will be this, and it should be scaled in the same way. So it's this hn divided by h max minus h min times y dim. So this is just such a way that the scaling is exactly the same way that it is. Now, if you want to make this three-dimensional, you could actually make it move forward and backward by making the radius also depend on that third dimension. And then you can get some feeling for what happens in 3D, or you could do something more fancy, maybe do this in a stereoscopic vision or something like that. You'll see. Okay, but let's do something simple. We do this, as I said, maybe let's do a simple check here. If d equals 1, I guess, one dimension, then we should do whatever we did before. And then we do an else. And then we're going to do this for the else case. And now we're going to copy this. And move it up here as well. And then we just leave that as the original xdim over 2 position. So then the code will still work for just 1D like we had it before, right? Okay, so let's see how much we crashed it. Here's our code. We can close that one off. We can try to compile it. And now we get our compilation errors, which are well, let's see where we're starting with here. HM, so this is, we forgot to do this. Then we just must be in the fourth routine. In line 23, oh yes, so this HM the equilibrium values we have to define as well in terms of D. For all particles, for all dimensions, I guess. And now we're going to do this funny thing again. We're just going to say d equals 0. Actually here. Here, d equals 0. Question mark, we get h0. Otherwise, we get 0. hm. Now hm, of course, is a function of actually no. What am I doing here? We already did this. Okay, so now I'm wondering, I guess it makes sense to keep this in here. So we just hm is just 0, that's fine. This is just where these things are sitting, else hm equals hm0, 0. That's all we need, I think. And then we're going to do this here, hm is 0, is this hm plus this, else you're going to set them to 0. Yeah, this is all that's needed, okay? That's just a smaller error. Now, what's the next one? Unexpected expression 50, line 50. What do we have in line 50? If n equals 0, else it looks like we're needing a bracket closed, else, okay, then of course we're going to run into some trouble, presumably. Oh, okay. Then we have this routine D2 apps, that's in line 65. So now we want to have the apps, D1 apps, and comma D2 apps also equal to 0. Apps. There we go, that's the 2 apps missed. Now, well, let's save this. Let's say clear here and see what we get, what's left in the errors. Not too many. GF. Every subscription is not an integer. Oh yes, this GF is of course not right. So GF of D, not of G. That's the dimension. Okay. And unexpected expression, there's something, well, with brackets again, presumably 94. Let's see, line 93, 94. If D equals 1, we missed the bracket closing here, else, okay, and then let's save this, clear this again, compile it. Oh, now we get all kinds of new errors. Let's see where they, not too many. Undefined identifier H. Oh yes, we don't need those anymore. We moved those a while back because we're not viewing them anymore. So these define graph and n can take out. And yes, here now we have trouble because this is not just here, but it's also in D dimension, right? Then we would have for int n equals D equals 0, D smaller d, d plus plus, and now we can have h0 of d, and I guess we should probably have, this is getting a little too much here. So now it will be twice as big, right? Because now we have, for all dimensions, we have everything in here. Probably we should do this here. So we start a new menu, and then we can define all those. And then we have our function in equilibrium, which will automatically put them in equilibrium. And then we do our end menu here. And then at least that's the nasty big function is kind of encapsulated out in its own right. Let's do this. Okay. So then we have our own little init values menu, and that will be nasty with all these data points now. I'm not sure if we need them all, but okay, we'll take it from there. Now, oh, we should see these dots here, so we need to save it first. And now let's see if we can compile it, and we get what error? That's not define menu, start menu. Sorry. Start menu. So now it compiles. Let's see what happens. So now we have our init values here separate, and that's a large nasty array. And let's see what happens here. Oh, I can't even move this. Will this give me? Oh. Not so used to these things. Ah, here we go. Ah, better. So this is now our position, velocity, age, velocity. So this is where they initially are. Let's have a look at our graph value. And the same thing applies still. We have to have our h min at, what did we say, -50 or so. They're sitting here. Well, let's see if they're still, well, they're still not doing anything, which is good. Oh, something happened. They moved. That's not good. Let's do init. Ah, something crashes them, moving them away. That's not good. Well, let's find out what we did wrong. So it looks like they all get so they start here like they should, but when they run, they run a little bit. That makes this nice and slow. Let's init this again. Let's init this, they're sitting there. Oh, they're jumping wildly. Let's init them. You should allow for single steps. That's probably a better idea if you do single steps to see how this is going wrong. At least the initial drawing still works. Let's figure out what else is going on here. So a good way to do this would be having the opportunity to just do a single step. I'm missing an E here. Single step version of this, and then single step. And here in our routine, we don't have just have done now, we also have a continuous, and then we have single step. And now let's just close this off for now. So now we're going to go Actually, should probably do this nanosleep. Anyway, just to kind of give us a little time to okay, so we do the nanostep in any case. That's not a bad thing. Now, let's do this else. Okay, now, if we want this to go, then we would do this or single step, and then we would set sig to 0 every time. So then we can go through it single step by single step. Now if we compile this and run this, we can go to the graph and now we can do this a single step at a time. So now we can see one step. The first thing that happens that the top ball gets moved off somewhere where it's not supposed to, and then the second time we move, this gets pulled up even more. Now it gets pulled up even more, and you know another single step, and this stuff gets pulled up a lot. Let's see if you make this H max big. Okay, they're sitting there. These get kind of pulled off to who knows where. But there's something that's wrong, particularly at the very top, where this now gets pulled off a lot, and who knows where these particles go. Okay, so that would suggest that something in our forcing routine happens at the very top, right? Where we define these particles. So let's have a look at what's happening here. So now we have our forcing routine for the zeroth particle. We set this to H0, which was supposed to be at 10. So this is supposed to be our fixed point. Otherwise, it's at 0. So 0 should be the value for H0 here. Okay. So that being the case, not clear what's going on here. So the forcing terms, why would this go? So we have the H minus 1, the previous particle, so to speak, that sits if n equals to 0. And a special routine. Else, this is for n not equal to 0, so it's a larger n. And this, I guess, should also be NP, not that it matters very much. Then this should count here. Else, if it's at NP minus 1, we just set it to be the plus 1. That's this special position, as it's n plus 1, right? Okay, so this all looks fine, but something's still wrong with that. I'm not sure. I don't think we've done anything here remarkably relevant, but let's compile this again, run this again. I guess you could set the hmin to -50 right away. So we have this. And this one particle gets moved out there. Is it this initial one? Let's do the init again. Maybe it's the bottom one that gets moved. Yeah, they all get moved up just a little bit, which is funny, but this particle is probably from down here. So let's count this. 1, 2, 3, 4, 5, 6, 7, 8, 9. And this must be the 10th particle. Let's init this again. Yep, there's a sitting. It's the bottom one that gets kicked off nastily. Okay, so something weird is happening down here, not up here. Okay. Let's see what we're doing at that point. So this is maybe calculating the forces for the bottom one. If n is np minus 1, then the plus 1 for all dimensions is set to the hn1. Else hpd is hn plus 1d. So what is going on here? This matters so much, but that is really odd. Well, let's see if we can reduce the number of particles. Let's init this. Now let's do a single step. Yeah, and the red one, the yellow one now gets kicked off. So it's something happening with the bottom one that's obviously wrong. Now the blue one gets kicked off. Now the red one gets kicked off. And then the red one will be gone. Well, actually, both of them are gone now. Okay, let's init this again. They're all sitting here at a single step. Something's happening to the bottom one here. It's just really, really wrong, right? What's happening with these is that, the way we've written this here now, we are running into trouble if two particles are sitting at the same position, right? So what we've done previously is that we just said, oh, these particles, the bottom particles, happen to sit at the same location, is not good, because now what we did is we divided by 0, right? So we have this, we put them at the same position, and this is HM or HP, right? Then, of course, what happens is that things just go wrong, right? So what happens then is that d2abs is 0, and we divide by d2abs, so there's 0 times something divided by 0, and that won't go well. And now the question is, how do we avoid that? And maybe the easiest thing is to just have different force laws for different parts of that routine, and then we don't have to worry about those endpoints. We would just say, if n equals 0, we have one force law, and else we say np minus 1, and p minus 1, then we do something else, and then we say else we're going to do this. And now we're going to modify this for the other two situations for force law, and that will be a way of getting rid of those nasty bits where the positions just happen to be right on top of each other. It's still it's physically not a problem if they're on top of each other because we don't really need the multiplication and division. We could just leave it in here, but we'll probably go into more general forces, and their forces they often have difficulty here. In fact, what we will do is we have force laws where we just divide by this L apps already, and then we don't have to do the specific division, which is often a nicer way of doing it. But for now, we're just going to leave out this first force if we're at the first one, because there won't be a first force. And if we're at the last one, we just remove the last force here, because the last force won't be there. And else we just do the whole thing. Let's see if this works. Close this and compile it. Oh, now we have an error. We've closed something somewhere 85. Where? What did we do wrong? If else, tab, something happened. Let's try this. What does this close off now? This is the end loop now. Somewhere we got rid of one bracket here. I'm not sure where that came from. This will close this off. And now it compiles and we get, let's have a look. We go to -50 here. Okay, let's do a single step. So something is wrong with our forcings, but not wrong in the same way as before. They all get pulled in the opposite direction. Let's make our time step much smaller. Let's init this. Running off. Let's make this. I wonder if the gravity just works in the wrong direction now. Let's make this big. With this. So it's not displaying it right. Let's init this again. Maybe what's happening is that these particles are. So this force law is not quite right. Let's move this out. So the other problem that we have right now is if two particles now get pulled on top of each other, bad things will happen, right? And that doesn't have to be the case if we remove these F bits. So this is obviously unnecessary. But could have done this before. Did I delete something too much? Apps, right? Okay. 2D, there we go. D2. Okay, over M, and the same thing right here. You can use this. Move this, and then move this. And remove those as well. And that should get rid of problems that arise from particles just having to bounce on top of each other. So we're now combining this one factor of 1 over this with our fourth law right away. Obviously that should be exactly the same thing, but let's just compile this. And now you can look at the things are not in equilibrium, they get kind of pulled upwards. And now they get kind of pulled in the opposite direction. We need to move them up a little bit. Not the way the particles, but we need to move up H max to 100. Now they're sitting there. Moving up all the way. And bad stuff's happening. Maybe the forces don't pull them in the same direction. Let's make the time step smaller. Make sure that doesn't cause anything. It's in it this. Moving slowly, but let's see if we can. Given this continuously, now we see them all pulling up, down, and up and down, bouncing up and down. See how much larger we have to make this. So we put this 200 and 200, and then we can see hopefully what's happening to them. Obviously, they get pulled in the wrong direction. Obviously being pulled in the wrong direction, and bad things happen with these. So some of the force laws don't seem to be storing but pushing away. Let's see what happens if we define our force G in the negative direction, which is I think we haven't done yet. The G force is defined up here. Let's just define this as plus. Let's see if that moves them in the right direction. And I think there seems to be something else not quite right. Well, we don't see anything here. What's going on? What? Okay, so now it does this. Oh. We're using this in the calculation of where the original position is supposed to be as well. Now it's falling down instead of moving up, of course. Let's do a minus here. See if that will set them in the original position. Graph. So this is now what they're doing. Now do a single step. Still being pulled upwards. Let's find out why that is. Well, I think we could try is just, well, first of all, we should have should have those k over m, of course, in here. I'm not sure why we don't have. G and address of G. So those should all be inside our GUI, so we can change them. Let's find out what's going on here. So now we have G and the k over m defined in here. So those are our graph values, and so they're getting pulled up now here by reasons that I'm not sure. So something pulls them in the upward direction. The forces are unbalanced. Let's see what happens if we set G to 0. And we init this again. Now, this is only the spring forces acting. And they're pulling stuff upward as one might have expected. But now let's do something funny. Let's put h0 to 0. And now go to the init values here. And let's go to our init, now the init value routine. Let's see if we can, here, we have the little bottom at the bottom. Okay, then we can make this more. But let's do init equilibrium. Everything is set to 0 now, because there is no gravity, so everything should be at 0. Let's init this. So now that looks like everything is moving. Now let's move one of those with some initial velocity in downward direction of, I don't know, 1, doesn't really matter. We need to init this now. So this one is now moving upward, and then what happens? So if that's moving upward, everything now becomes unstable. So it looks like our springs aren't attractive springs, but they're repulsive springs. So there looks like we got our directions wrong. Because, so let's see, when we have our forces, yeah, so it's in the direction of D, it should be the negative of that direction, right? It should, the force should be in the opposite direction of the displacement. If the displacement is measured between, so how is the displacement measured? It's measured between the current one and the previous one, so the points, it points into the direction of, well, what did we say? So it's the where it's pointing to minus this. That should be one that points in the direction of the upward rod. So that is the direction it should be pointing into, right? That's what we were thinking. So what should happen is just this one thing, it moves out and it kind of pulls the other stuff with it a little bit, but that's not what we're seeing here. And why is this not what we're seeing? So it should be, so what we're thinking we're doing is we have the displacements D1 and D2 here, and these displacements are in the direction, so this D1 vector, if I start this at Hn, it should point in the direction of Hm, right? So, or Hp, so it should point in the direction it is. So there should be a force in that direction. And what we didn't change is our signs here. They should just be in the same direction. They're now completely symmetric, whether that, because we've changed the way they're pointing, These are now completely symmetric, and that should not matter anymore. Let's try this again. That could well be what's causing a lot of our troubles here. I think now we changed, okay, so now we changed around the directions, and so what's happening here? Okay. What we haven't, so we've turned around our G, which I think we shouldn't have done. Then we're trying to fix it. But also, what we didn't do is I think we did this too many times. This should still work here. We still need this in the case for H0, so that the top one still has to be held, still has to hold on. Okay, so there's two things we need to change. We need to change this back to minus, and in the equilibrium, we got the sign wrong, which we switched around carelessly to try to fix stuff. And now, let's have a look. Maybe compile this. Now we hang this up again. Graph both on H min is at minus 50. Now so nothing is happening, which is good, which is what we were hoping. So now we can see if it still does the, we go to the init values. I prefer this on my Linux computer, but anyway, so we have some values here. We set this velocity to, what did we do? We set it to 10 or something like this. And then we go to the init values, and now it's bouncing around again. But what we should also be able to do, instead of doing this now to 10, should be able to change this one to 10. And do init. And now it doesn't need a side racing. And so this is actually what it's doing. So we have a side rate bounce now. So there we can see actually that this 2D structure. So we have this thing. It started off, we should need to slow this down a little bit. So now we're kicking it, and now it can actually move sideways here. Right? That's what we were hoping for, that we give it a sideway motion, and that sideway motion would now be translated to top here. And that's exactly what's happening. It induced some kind of wiggle here, and that wiggle is now produced here, so it's doing this, and now you can see this. Now we have a proper motion, and you can see sort of pendulum motion, but not quite, created by this wiggly notion here. Okay, so that's much better. And okay, so after our few little mistakes in getting this forcing exactly right, now we have this thing hanging here, and it's working in, well, we see that it's working in 2 dimensions. I believe it will work in any number of dimensions now. We have a multi-dimensional thing, and we can see it wiggling here in a however fancy way, fashion, form, right? Now we can put H0 down a little bit to, I don't know, 9. Which should just drop it, right? This takes this whole thing, it just drops it down a little bit. And now we have this overall wiggly motion. One thing that, of course, it doesn't have is any friction in there. And also, what one could do now is one could try, I don't know, wiggling the top position here, right? So you could sideways wiggle this thing and see what happens, right? and then we could change that initial top motion and see how that evolves, right? So that would be a good homework problem, I think. Just take the top point and oscillate it, and maybe think about introducing some form of useful friction terms that would be physically inspired. And that should be the homework. I'll write that up into a homework problem that you can then submit properly on Long Kappa. Okay, so there'll be lots of questions, I'm sure. I heard that the university is closed on Wednesday as well, but it should be okay on Thursday, I hope. So we'll see you, and then, well, you can see if you've been able to watch this video and if you've been able to follow through on this. As always, I make sure that this code will be available on the Mini. It's not on the Mini yet, but I'm just going to copy it over in a moment, so you can download this code if you want to, and then you can have this object to play with. So if we init this back to equilibrium, and then we init it, nothing happens, right? So now we can do fun things where we have bring H0 back to 10, right? And now we introduce this wiggly bit, and then we can introduce, well, we could also start wiggling at the top by giving this one a top velocity in the other direction, right? The second direction here, 10. Let's init this now. And yep, funny stuff happens. But I think it'd be really fun to see what happens if you oscillate this at the top here. So this will be your homework. Just take this top part, move this around, and see what the response of this hanging string is. Okay. And so that's the problem for now. And I'm going to stop it right here, I think. And I'll see you on Thursday, and you'll see how this all works. Okay, well, wish us luck with this. See you on Thursday.